Okay, guys, good morning. Let's figure out why we're just getting here mostly. Any questions before we start? Good?
The bottom problem right there.
Yes, we're going to do this one here. I don't think we did it last time. We'll pick up here. We have an alkyne. The terminal hydrogen is acidic enough that we can remove with a strong base. Ethyl lithium is a very strong base. It's a carbanion. These electrons take the H. These electrons stay behind. Good old acid-base reaction. I'll just show that as phenyl. Now we have a lone pair on the carbon, and that's a minus charge. We generated our acetylene, or acetylide anion, it's called. It's the anion of your sp carbon. Now we throw in dimethyl sulfate. Dimethyl sulfate, that's that there. These electrons will then attack the carbon and kick off the leaving group. And we end up with that there. This looks a little bare to me, so sometimes I may like draw an AME or something, but what did we make? We made that bond there. And we went from a terminal alkyne to an internal alkyne. It's just a good old, we generate the nucleophile, and then we use dimethyl sulfate as a methylating agent. June, how'd you do? Any questions about that one? Okay, mostly review, yeah. Use of dimethyl sulfate, a little new, but it's analogous to a tosylate. Over here, we have alcohol HF. HF is a strong acid. It's strong enough to be considered a strong acid. F minus will not react as a nucleophile, just like an organic 1. F minus is a poor nucleophile. So we can envision protonating. Okay, we can envision that. What's going to happen next? Well, forget about the F minus. It does nothing. What can this do next? It can ionize if we're going to do anything. Okay. We could get positive charge here, plus water. So we lose water. Is F minus going to attack there? No, F minus never does anything. You're not going to get a substitution product. Instead, we're going to get what type of product? Well, if we're under numeral 2, we're elimination, just like sulfuric. F minus will act as a base and take the beta hydrogen. These electrons move in, and ultimately we get alkene. We have dehydrated the alcohol. And right here, what are we reforming? Well, yes, actually. So HF is actually what in this reaction? It's actually the catalyst, because we're reforming it. We get this plus HF. Question?
How did you know to take that beta hydrogen instead of the other beta hydrogen?
Good question. We should have mentioned that. One down here. That's kind of odd. Is this really a bond? Well, you know, that's me. All right. If I try to draw it too precisely, it looks funny. All right. 6-membered ring. Why not take one of these? Put double bonding down here. What would that alkene look like? Double bond there, methyl there. Okay. Which one you're going to get? The one we drew or the one on the right? Why not that one?
It's more substituted, the one on the left.
This one is more substituted. It's more stable. We call this one the what product? State-step product. That was the Hoffman. What we're doing elimination. We're doing E1 or E2?
E2.
No, E2 requires a strong base. There's no strong base. This is acid. You can't have a strong base in the presence of acid. It's an E1. It involved making the carbocation. E2 doesn't involve a carbocation. E1 always gives which product? most stable alkene you can draw because it's equilibrium bound. Okay. So you get the Zaitsev product, not the Hoffman. That's right. Always give the thermodynamic product. That's the thermodynamic product, meaning that's the most stable product. Questions on that page?
I had a question on the
Uh-huh.
that level. So how would you protonate that alcohol because isn't chlorine more electronegative than oxygen? So
I can't quite do it.
so how would you be able to protonate the alcohol because isn't chlorine more electronegative than oxygen? So how would it pull away that hydrogen?
Well, HF is an acid. I think you could ask that same question about any protonation you do, because anytime you do a protonation, well, no, not always. Sometimes you're going, okay. Strong acids. What happens if you put a strong acid in water? That's the terminology. What happens? The oxygen takes the H, and the H sits with the oxygen. I mean, if you put HF in water, you're going to get H3O plus what? F minus. They don't tell you this in Gen Chem, but you're protonating the oxygen. It's the same exact way. These electrons take the H plus, or you can show it covalently. Any way you want to do it. I do it both ways in here. Now the H sits with the H plus. I mean, the H sits with the oxygen. That's exactly what we did here. Didn't we? We protonated the oxygen. Just as if you would have put it in water and you protonate water. The important question is the equilibrium. You're maybe asking, well, why doesn't it go back this way? Well, that's just equilibrium. You can get into it. We call it a strong acid. We know it's going to come this way. You can have your pKa's of this and judge the equilibrium and use pKa's to judge which way it's going to go. At some point, it's not going to go that way, and then your answer will be super valid. But in this case, it is going that way. Okay, good question. Now, HF may not be as strong as like HI, but it's strong enough to do the job. Question?
For the same mechanism, like if we were to draw it mechanistically, would you want us to show the carbocation rearrangement even if it gives you the same?
That's a good point. It could rearrange, but it would be the same product. You would then just do the beta elimination from the other after it rearranged. Yes. There's two types of questions. That's a predictive product question. You could get that right and have no clue what the mechanism is, because I would just be grading you, did you get the predictive product right? Okay. It wasn't really a mechanism question. Although mechanism is very important to helping you predict the product, right? Okay, how about this one here? I got an alcohol. That's the only reactivity I know. We don't know any reactivity for benzene rings. Alcohol reactions. We got phosphorus. It's not a strong acid, but it's strong enough. Okay, it was on the list in organic 1. Okay, what type of mechanism do you think is going to be here? Substitution, elimination. Elimination. Because there ain't no nucleophile to do substitution. Phosphate is not going to act as a nucleophile. It's a classical elimination, just like we said would happen on the previous page. You're going to dehydrate, make an alkene. Are we going to make the alkene over here or over here?
Left.
They both would be disubstituted. Is there any difference between the two?
Yes.
We can draw them both here. We have that alkene. I'm not going to draw in the phenyl, but that's very important. Or we could have that alkene, I believe. OH used to be here. Yeah. Okay? They're both disubstituted. But is there any difference other than that that we can use to assess stability? Yes, this double bond is conjugated with the benzene ring. That double bond is not. There's no p orbital here. Which is better? A conjugated system or a non-conjugated? Conjugation is going to be better. So that's the answer to how you determine which is most stable. Now I drew this trans. Could we draw it cis? Is the product trans or cis? Why trans? Because trans is more stable than cis. E1 always gives the most stable. That's it. Boom. Don't have to worry about anticoplanar or nothing. Because E1 is driven by thermodynamics, and the most stable is going to win out. Okay. B. B implies that there was an A. And A and B implies that we're under something. What are we under? B is another way to dehydrate an alcohol. We can use pocylpyridine. Okay, a lot of people call it pocyl. It's phosphorus oxychloride. But it looks like it reads pocyl. Pocylpyridine. This will be an E2 mechanism. This is a way to do E2. For example, if you have a primary alcohol and you want to dehydrate it to the alkene, it's actually kind of difficult using acid. Because this implies you're going to make carbocation. This is E1. You don't want to make carbocation there. It's going to be very difficult. And while sometimes it might work, I usually told you don't ever do it. Okay? Pocylpyridine is an easier way to dehydrate like a primary alcohol because it goes by an E2 mechanism. And we don't form a carbocation. So let's look at this. Pocyl is analogous to lactonyl chloride. It's actually analogous to PCl3, except it's got the double bond oxygen. These electrons start here by attacking the phosphorus. What do you want to do? Electrons up onto the oxygen. Okay, we get phosphorus, electrons up, oxygen becomes minus. We got chlorine, chlorine, chlorine. We got oxygen. I'm just going to call all that R. There's H there. We didn't lose the H. There's still one lone pair left, and that's a positive charge. So nucleophilic addition of the oxygen to the phosphorus. The pi bond moved on to the oxygen, consistent with what we saw before, yeah? At this point, we've got to take care of that proton. Actually, last time I didn't do it. I'm going to go ahead and do this. These electrons can come back down and kick off one of the chlorines. And if we do that elimination step, we can have a phosphorus double bond O, two chlorines, oxygen, R, H plus, and Cl minus. Additional elimination to get overall is a two-step substitution. We replace one of the chlorines with an alcohol. At this point, I really we can't use R. I need our carbon chain here. Unless we take care of the H. Carbon chain is pretty long. 1, 2, 3, 4, 5. Okay. All right, I'm going to go ahead and take care of this proton now. You know how sometimes you just put things off? It's time to deal with it. Once this adds, this H becomes acidic because it's on a positive oxygen. Okay, just like H3O plus is the H is on a positive oxygen. Once it becomes acidic, pyridine is going to act as a base. Now, some people will take the H off here. I'm going to take it off here. Pyridine, these electrons take the H, electrons stay behind, and we can take care of that proton and we get to Now we have the electrons back here. That's a neutral oxygen. We have Cl minus, but we also made a protonated pyridine. Okay? Plus protonated pyridine. You got this already drawn. Okay. That's a positive charge. Now, what are we trying to accomplish? We're trying to eliminate the oxygen and put a double bond in here. Well, at this point is where you can do it. Now you take actually another pyridine, and it acts as a base. It's fairly weak, but it's strong enough to do E2. Now we can take one of the H's. Now these can move in and kick that off. Is that oxygen a decent leaving group? Think about it. How do you make oxygen a better leaving group? Protonated. Well, it was protonated over there. Yeah, but we got a base. And anytime you got a base around, it's going to take the H, and it ain't going to wait. But look at this. This oxygen is bonded to, like, all this electronegative. If this was a sulfur and with two oxygen double bonds, that'd be like a tosylate. This is analogous to a tosylate. This will leave in a rate-determining step. Let's do it and look at the leaving group. First off, what does this mechanism look like? E1 or E2?
E2.
That's your classical E2. All inserted. What does that give? We now have double bond. It gives product. 1, 2, 3. Yeah, double bond here. Plus, what was the leaving group? Phosphorus, O minus, chlorine, and chlorine. But this is very stabilized relatively. You can actually do resonance structure. That is a lot like tosylate being the leaving group. It's a phosphorus-based thing. And the end result is that will leave and presence of the strong enough base, we can do an E2. And nowhere up here did I form a carbocation. That proton will plague us all the way through the course. When do you remove it? Ultimately, you remove it as soon as it becomes acidic. Well, hot and cold are going to react as soon as they start coming together. Okay. Electricity reacts. Electrical reaction happens as soon. It's not going to sit there and wait until you tell it to happen. Okay, you need to digest this. Ultimately, that's an E2. The OH was ultimately activated as a dichlorophosphate ester. That's a dichlorophosphate ester, similar to a tosylate. That's how we ultimately activated it. Now we can do an E2, where you can't just take the alcohol and do an E2. OH ain't going to leave, but the O bond to the phosphorus will. Okay, this is polypyridine. It's an E2. Because it's an E2, we have to remember the stereochemical requirement for an E2, which is what? The leaving group and the beta hydrogen have to be what orientation? They have to be coplanar, your transcoplanar being highly preferred, or anticoplanar, right? Okay. That wasn't important here. When is that important? Well, for example, down here. Show the product of this first reaction down here. And think about it. And think about the next one. Okay, there's some typical questions that are usually asked here. I'll just wait for you to ask them. Okay? All right. First off, for a no carbon, what does polypyridine do to an alcohol? Rosario? Dehydrates. To make what? Alkene. Boom. There you go. There's your starting point. Okay. What mechanism is it? E2. Boom. No carbon. Okay. Now we can do it. You need to be able to do it. Okay. Phosphoryridine. Let's see. Alkene, Satiev, Hoffman. Where do we want to make double bond is preferential. Top or side? Side. Okay. Well, do we just draw that and say, hey, I'm going to have that there? Well, hold on. This becomes activated. There's no change in stereochemistry here. The H is here. After that's activated, that's the leaving group. Here's the H. Are those transcoplanar?
Yes, sir.
Yes. Okay. When this is axial or equatorial?
Axial.
Axial. Yes. When this is axial, they're going to be, that's also will be axial, and they'll be transcoplanar. So yeah, we can do that. There's your product for here. There's no reason you can't get the Satiev product. But what about the one below? One below, in which everything is trans here, the H is cis to what's going to leave.
So.
And actually up here, you're going to get of the 3 beta hydrogens total that are there, which one is anticoplanar or transcoplanar to the ultimate leaving group? This one. And so down here, all right, that's the top product. Down here, the product is actually double bond up here. And this methyl remains here. And you keep the stereochemistry. No chemistry takes place here. That stereochemistry is still there. You get double bond up here. Because the fact that this is anticoplanar is going to outweigh getting the Satiev product. You actually get Hoffman here, because you have to meet typically stereochemical requirements. Yes, you can do a syn-coplanar elimination, but it ain't going to happen if somewhere else you can do a transcoplanar. But hopefully that makes sense, just like what we did in organic 1, yeah? Okay, questions? Green sheet, what's the next topic? We're just kind of coming down the arrows. O-alkylation, formation of ethers. Okay? And here we are. By the way, I brought my textbook when I was an undergraduate. I don't know if I've showed you the organic 1. Still have it. It's kind of falling apart here. It's actually a quiz. 1993. Made a 7 out of 10. Man, that's bad. Hey, I had a 10. And a 9. All right. In the end, you need to make good use of your textbook. If at the end of the course your textbook looks brand new, you're either very good at keeping things safe, or you're not really using it that much. Okay. O-alkylation of alcohol, synthesis of ethers, Williamson ether synthesis. We saw this in organic 1. My guys, formation of alkoxide anions. Okay. Here the oxygen is not going to leave, but it's going to act as a nucleophile. Okay. Typically, you can do either mechanism, but for the Williamson ether, typically it's SN2. You want this to become a stronger nucleophile. You do that by removing the H. If you want to make this a leaving group, you protonate it. If you want to make it a better nucleophile, you deprotonate it. Most traditional way to deprotonate is to react it with sodium metal. Okay? That'll give you the sodium alkoxide. Now, of course, that's just formula. It's really minus and plus, right? We have the alkoxide. Alcohol, alkoxide, with the IDE ending, indicating the negative charge. You also form hydrogen, H2. If you want to balance this reaction, go for it. Okay? Not balanced as shown. We did this in lab. We cut some sodium and put it in alcohol. What did it do? Started bubbling? Yeah. What are the bubbles? Hydrogen gas. You can also react this, if this is H, that's water, you can react sodium with water, but it's pretty violent. A little fire?
Yeah.
Yeah? Okay. So this is a common way. It's actually a redox reaction. Because here the sodium is 0, it's a metal, now it's +1. Hydrogen is +1 here, now it's an element, so it's 0. So you got redox going on. And we typically, it's hard to show redox reaction mechanisms because they're usually radical mechanisms. And they're often not well known. This down here is another way, and this is a more traditional acid-base reaction. Sodium hydride, I don't think we've ever seen that. You can have that. Sodium is plus, that means the H is what? The H is actually minus. It has a lone pair and thus minus. This can't exist. Sodium hydride can exist. Draw the bond in here. These electrons take the H. These electrons stay behind. What does that give? It gives O minus. It gives hydrogen. And the sodium plus is going to sit with the O minus. So that's a more traditional acid-base reaction where we can show our standard acid-base mechanism. But at the introductory level, usually you see sodium used. I show sodium hydride because it just makes perfectly good sense. And you might see it, but sodium is just more common. Sometimes you see sodium hydride used to deprotonate the alkyne H. Some textbooks will use it. Other textbooks like to use lithium to do that, like I did earlier. Okay. And once we deprotonate, make the alkoxide, then the alkoxide can act as a nucleophile. For example, here. All right, what does sodium do to the alcohol? Well, we already showed that. Okay, we can just, in our mind, if we're not having to show mechanism, we can just say, okay, this makes the alkoxide, right? Now we throw in this, it's a carbon with a good leaving group, that's what you see here. A decent leaving group. These electrons then attack here, kick the leaving group off, and what do we get? Okay, you can draw the ring out, or you can just say phenyl. We made this bond here. Two lone pairs left. CH2 phenyl, right? CH2 phenyl. I see students just don't show the CH2. It's there. That's what the nucleophile is bonding to, the CH2. Any change in stereochemistry at this carbon? No. We did no chemistry there. Stereochemistry is still the same here. What if we had stereochemistry at that carbon? That's where we would get inversion. But there's no stereochemistry in this example. I'll just not cover it. Okay, phenols. OH on the ring. These are more acidic. pK about 8 to 10. Or even lower, depending on substituents. Phenols are acidic enough that you can use hydroxide to deprotonate them. You cannot use hydroxide with regular alcohols. You can with phenols. Okay? And so it's our good old acid-base mechanism. Hydroxide is strong enough. These electrons take the H. These electrons stay behind. You get this plus water, right? Of course, that's minus and plus. What do we call this here? That's a phenol. What do you want to call the anion? Alcohol, alkoxide, phenol, phenoxide. You can generate the phenoxide using the weaker base. So, look at this reaction. Treat this with KOH. Where's the most acidic hydrogen in? Well, it's the phenol, because all the other H's are on carbons. Okay? So we deprotonate, okay, just like up there. Make minus. The potassium sits with this. If you want to show an end result fully balanced. Then we throw in a carbon with a leaving group. Do we have that? Yes, we're going to tosylate these electrons in here, kick off the leaving group. But here we have stereochemistry. So what's that product going to look like?
Still forward.
I believe it's going to look like this. That's a D. Is that right?
Because you turn the right molecule.
Is that right? Is this RS? Oxygen 1, carbon 2. D or H, which is higher priority? D, it's got more neutrons. Okay, isotopes, a higher neutron gets priority. 1, 2, 3. H in the back, what is this? S? As long as the new group still has high priority, like the one that was replaced, you can do what I'm doing. Does it? Is a new group still high priority? Yes. Okay. What is this one? R. See? Inversion. Inverted, right? If you want to draw a dash, you can draw a structure with a dash. Don't fall into the trap, though, because that's bold. It has to be dash. No, it has to be R. There's a variety of ways you can show R. Now, the way I did it, you can get tricked sometimes. For example, what if the nucleophile was like H minus, and all this was H? Well, then this would not be 1. That would actually be 1. And I'll blow you mind with this. You can actually do an inversion, but still go from S to S with that type of scenario. All right. So hopefully you'll never see one like that. If you go back, just basically, okay. If the leaving group is there, how does the nucleophile come in? Does it come in over here? It comes in here. So if we show that carbon right here, the nucleophile is going to be over here. What happens, it pushes the other two groups sort of that way. So the alpha, instead of this way, it pushes it over there. The D, well, I've kind of got that turned a little bit. The D can be forward, but when the nucleophile comes in, it just pushes it that way. The D is still forward, it's just, but it has been inverted. Now if you want to see it the other way, you can say, well, here the D is forward, and when it comes in, now it's back. It's just because I just turned the view. Here it's forward, it's still forward. But for my view, it's back. Okay? But see, it's all there. Think about it. Here we need to be able to go backwards, and we're going to be doing more and more synthesis, going backwards. Can you provide a Williamson ether synthesis for this compound? That is, can you say here, I would make this by reacting this with this. How could we make this ether? What are the two components of an ether synthesis? The O-, which is the nucleophile, and then a carbon with a leaving group. One fragment has the O minus, one fragment has the leaving group. And we make the O carbon bond. But you can make this O carbon bond or you can make this O carbon bond. Which bond do you want to make here? Well, let's do them both and then see which one looks better. I'm going to put a methyl here so we... What if we say we take... What if we make this bond first? We take that, and then we have this portion. This portion is going to have the leaving group. What's your favorite leaving group? Somebody said iodine? Okay. All right. Now we can potentially, can we make that bond? Can this come in here and kick that off? No, why not? You don't do SN2 on a tertiary carbon. No. No matter what the leaving group is. So let's consider making this bond over here. That would come from having the O minus on that fragment. And then over here, which is just a methyl, and you see why I drew the methyl, because if I didn't draw it in, I'd be like, well, there's your methyl. It's a methyl, but what do we need on the methyl? A leaving group, like an iodine, or whatever your favorite leaving group. This could attack the methyl. Now you can draw this out. It's a CH3. Okay. Attacking the methyl. Kick off the leaving group. Does this look reasonable? Yes, that's a good old SN2. We're attacking not even a primary carbon. This is just a methyl. That's not even classified as primary. It's very easy. Methyl iodide is very reactive in SN2 reactions. And this will give this check. That will not work. So this is how you design your reaction. But if we set it up in a nice synthesis, we sort of say, okay, I'm going to start with this alcohol, because you need to show how you generate your anion. I'm going to react this with maybe sodium. That's going to give the O minus plus sodium. Then we react this with methyl iodide, often just shown like that. And there's our product. Okay? So you show each step in your multi-step synthesis. And that's just 2 steps. Question?
Is there a reason you couldn't do SN1 on white?
Typically, Williamson ether synthesis is often SN2. It doesn't mean it can't be SN1. You want to do SN1 over here? Okay, you can do SN1 with that, but do you want to use this for SN1? This is strong. Strong nucleophile is going to want to go SN2. If you react these, it's not going to do no SN2. These will react to give a product. What reaction will these two undergo to? What's the product of these two? Not a substitution. This is going to give E2, right? This will act as a base. You'll end up with that alkene. Because it will go bimolecular. Since it can't do SN2, it will go E2. That's going to eliminate, not substitute. Now, if you use methanol, the weaker nucleophile, you could maybe do an SN1. I agree. Typically, in most textbooks, the way it's presented, you always sort of design an SN2 reaction. So, choice of route is important. There's one below that you can do on your own, and we'll look at next time. Down here, explain why the Williamson ether synthesis below is not logical. Why is that no good?
PKN.
Anybody got it? How's that look good?
Yeah, look at the box like that.
Yeah, it's more acidic.
It looks like we're saying that the base is going to deprotonate the phenol, and then the phenol attacks here, and we make this bond. The problem with this is that's not the most acidic H. The most acidic H is your carboxylic acid. The base will take this using one equivalent. Now you might could use two equivalents and get it to then deprotonate that. But then you have to ask this oxygen not to attack. So if you use one equivalent, you're going to deprotonate here. Phenols that has a pK of about 8 to 10. This has a pK of what? About 4 to 5. pKa's are listed in the back of your lab manual. Okay. You do need to always start learning your pKa's. Alcohols, phenols, carboxylic acid. Okay, you can do all this chemistry with the analogous sulfur. Okay. Sulfur is under oxygen in the periodic table. The chemistry is very, very similar. For example, you can deprotonate this with the hydroxide and make the trying to think of the most common name to call it. Let's call it the sulfur anion. How about that? Sulfur anion, and then this can come in here and kick off the chlorine. We can make that bond there. So you can also do this with sulfur. And actually, the SH here is more acidic than the OH. Analogous sulfur compounds tend to be more acidic, so they're even easier to deprotonate. Okay, next on the green sheet. Actually, I'm going to skip. I'm not going to do oxidation. Oxidation would be the fourth of the group up top. I'm going to skip down to chemistry of ethers. We'll do oxidation of alcohols a little bit later. I think you already have the handout. Chemistry of ethers and epoxides. First with ethers. Ethers tend to be pretty unreactive. They tend to be end products. The most common reaction to ethers is cleavage. Cleavage of an ether. You can also call it dealkylation, because that's ultimately what we're going to do. We're going to remove an alkyl group. We're actually going back to like the starting materials for the Williams and ether synthesis. We're going to go back to an alcohol and maybe an alkyl halide. Those two starting materials. You take this ether here, react it with HBr, what can we do? Well, let's approach it as just, well, what can you do? Forget about what it says up there. Mechanistically, what can happen first?
SN1.
Protonate the oxygen. We've got H plus, Br minus. These electrons can become protonated. Okay. By the way, I don't have to talk about equilibria. The question was asked, why does it come this way? Anytime we protonate, it's always an equilibrium reaction. That is, the Br minus can then take the H back and go back here. This is equilibrium. Okay? But from this structure, we can then perhaps move on. Okay, there we go. We can protonate. What can we do next? That is, instead of going backwards, how can we go forward somehow?
SN1 or SN2.
We do have Br minus. Okay? Think of your two substitution mechanisms. Well, here's what's going to happen here. This thing's going to, the oxygen is going to leave a carbon. Is the oxygen going to leave that carbon on the right or the one on the left? It's going to leave the one on the left. It's going to leave And what's that going to give? It's going to give that cation plus what? Plus, okay? See, it looks naked without the amidamine. All right, that's a methyl on the end. Methanol. It's a methyl on the end. Okay? Now, what can attack the plus? Yes. And these are your two products that come here, and we have cleaved the ether. We've cleaved it. You get these two products, and now we can talk about what's written up there and put it into context and start looking at some guidelines. Question?
Couldn't you use the bromine to attack the methyl on the right and then take off
You could. We're going to have choices. And we're going to say why. Okay? Certainly could. Question? Yes. Yes. Okay. This is an example of an ether cleavage. Look, we actually go back to an alcohol here. We could go this way. If we deprotonated, well, you got a problem though, because that's tertiary, so it ain't really going to go back. But it is the two things. It's your alcohol and like an alkyl halide. This is an ether cleavage. It's about the only thing you can do with ethers. It's often not done because this is how you make ethers. Nobody's going to make the ether and then turn around and go backwards. But it's still very common. It's seen in drug metabolism. And it's just a reaction we need to know, because it also helps us practice our basic understanding and etc. Okay, it gives an alcohol and alkyl halide, two smaller products. There they are. But which alcohol and which alkyl halide? It depends on the mechanism. What mechanism did we do? Leaving group leaves, we make cation, then something attacks.
SN2.
We did SN1. Because that was ultimately the leaving group after we protonated it. It left, and under my hand now is the bromine. The bromine substituted the leaving group, but by an SN1, carbocation. Okay? But we could do SN2. Here's your rules. When a tertiary reaction site is present, always go SN1. Did we have a tertiary reaction site present? These are your two reaction sites. Is one of those tertiary? Yes. So what mechanism are we going to do? Like we did. If no tertiary site present, then we'll do SN2. Stuff?
Does this reaction always need to be under heat in order to occur?
A lot of times, but it depends on, it doesn't have to be, but often it is. Especially if it starts going to only have to be SN2, because SN1s tend to be easier. You remember when we did it in lab, it was so fast we just put it in the cell phone and it was done? Yeah. SN2s tend to require a little bit more heat, because that rate determining step, pushing off that leaving group, is just a little more difficult. Question?
I thought bromine was considered strong for while and you couldn't do SN1 stronger.
You mean bromide? Bromide strong? Okay. It is strong according to our general definition in Organic 1. I said strong as anions and sp3 nitrogens. There are some exceptions. It's not that strong. It's actually borderline. Because remember, it is the conjugate base of a strong acid, which means it's very stable. Okay? So it's kind of an exception. Really keep in mind relative. For example, this is stronger than Cl minus. Okay? Sometimes it can do either, you know. A lot of the things, statements I make are very general, and then you'll find exceptions, but it gets us started. Okay.
Is that why primary alcohol is incompatible with the Lucas test? What you said earlier about SN2 requiring more heat?
Yes, because SN2 typically requires heat. And the SN1, Lucas, because you're doing it at room temperature, SN2 is difficult. It usually goes by SN1. And since it's SN1, primary alcohol is not going to react. Yes. If you start heating the Lucas, primary will react, but it'll probably go by SN2. That's going to be tough because you got Cl minus. So, you know, there's all this. Yeah, buts. Okay. Let's try the next one. What if we react this with HBr? What do we expect? Well, we can protonate. I assume everybody can protonate, so I'm just going to do that. We got Br minus. Okay, the leaving group can leave that carbon or this one. What are we going to do here? What mechanism we want to do? SN2, because I don't see a tertiary site. SN2. Since it's SN2, which carbon are we going to attack by SN2? Right or left? Right, less sterically hindered. This attacks the methyl. I'm going to draw that in as an ME. We kick the leaving group off the methyl, and we get, see up here, that's the LG. We get the LG, the leaving group, plus what? Methyl bromide, methyl bonded to bromine. There's our two cleavage products. This mechanism was what? SN2, because our rule tells us if there's no tertiary site, we do SN2. And SN2, you attack the least sterically hindered site, because SN2 is governed by sterics largely. Okay? Now this is sort of my rule. Some books go with this. Some textbooks actually will make it so vague you don't know what to do. I'm trying to give you a clear pathway. This is what I want you to do. Now, could this go the other way? Sure, but there's so many variables. How are we going to know? This is the way I want you to do it. And some textbooks actually state the rule like this. Okay. Where are we at? We have lab this afternoon. We'll meet upstairs.